In this lecture, we're going to discuss virtual memory. I've broken this lecture up into several parts because it's rather long. So let's get rolling. So first off, when code executes, it needs to be in memory, but the entire program is often not used. Sometimes error codes, data structures, code doesn't get pulled in. So we don't need it all at the same time. We need to consider the ability to execute a partially loaded program. This allows us to have programs that are no longer constrained by limits of physical memory. Each program takes less memory while running, which means more programs can run at the same time. This increases utilization and throughput with the CPU, but doesn't increase response time or turnaround time. Less I/O is needed to load or swap programs into memory, and therefore each program runs faster. Virtual memory is the separation of loose or logical memory from physical memory. Only part of the program needs to be in memory. The logical address space can therefore be much larger than the physical address space, and it allows address spaces to be shared by several processes. It allows for more efficient process creation, programs running concurrently, and less I/O. So let's talk about a logical view of how process is stored in memory. Usually we start at address 0, and its contiguous addresses from till end of space, to the end of the memory space. That's how the programmer would see it. Meanwhile, physical memory is organized in page frames. The MMU must map logical drives to physical drives. Virtual memory can be implemented via demand paging and demand segmentation as two possible ways. So, virtual memory that is larger than physical memory, we have our virtual memory page table, a memory map into our physical memory, and that, using the prior structures we talked to, maps to actual disk space. Or rather, memory space, sorry. So we're going to discuss a virtual address space here. We usually design our logical address space, and the stack starts at the top, and it grows down while the heap grows up. Heap is for allocated memory. This maximizes space use. The unused address space for the heap and the stack are in between, and no physical memory is needed until one of these grows beyond a page boundary. This enables sparse address spaces with holes left for growth and dynamically linked libraries. System libraries shared via mapping into a virtual address space, and shared memory by mapping pages pages with read-write capability into our virtual address space. Pages can be shared during fork, speeding up process creation, or the Windows equivalent, for example. So the way shared libraries work is basically we'd have what's designated as a shared library in our space, and then shared libraries separately in actual memory, and it can be used by multiple processes. So some options. Demand paging. We could bring the entire process to memory at load time, or bring a page into memory only when it's needed. There are definite efficiency differences here. In the demand paging, less I/O is needed, no unnecessary I/O. It requires less memory, the response is much faster, and it can handle more users. It's similar to paging systems with swapping. A page is needed and a reference to it, and if we have an invalid reference, we abort it. If it's not in memory, we bring it into memory. We could have a lazy swapper that never swaps a page into memory unless the page will be needed, and a swapper that deals with pages is called a pager. With a swapping, a pager guesses which page will be used before swapping out again. Instead, the pager brings in only those pages into memory. How do we determine that set of pages? Well, we'll need new functionality to implement demand paging. Okay? If pages are needed are already memory resident, then we don't treat it any differently than non-demand paging. If pages are needed and not memory resident, we need to detect and load the page into memory from storage without changing program behavior and without having to change the code. And that's the key part, without having to change the code. So with each page table entry, a valid-invalid bit is associated. V as invalid, I as in not in memory. And from there, initially the valid bit is set to invalid. So here's an example of a snapshot. During MMU address translation, if the bit is invalid, we cause a page fault. So here's an example. We've got our page table. We've got our logical memory. We've got our page table and our physical memory. Here, where it's I means it's not in memory now. So currently what is in memory is A, C, and F. And all of it's stored on disk, so if we need to bring it in, we can. So when there's a page fault, the first reference to the page causes a fault to get trapped. The operating system looks at another table to decide if it's an invalid reference, we abort it. If it's not in memory, we're going to find a free frame. We're going to swap the page into the frame via a disk operation and reset the table to indicate the page is now in memory by setting the validation bit to V, and then restart the instruction that caused the fault. So here's a diagram. So we try to load from memory. We check the page table. If it's invalid, we trap or throw an exception, however you want to refer to it. To the operating system then finds the page on backing store, brings it into the free frame in physical memory, back into the page table, and then it restarts the instruction. So from the process's point of view, it's always in memory. So in an extreme case, we start with no pages in memory, and the OS sets the instruction pointer to the first instruction of process that's and a non-memory resident fault occurs. Every other process pages on first access as well. This is called pure demand paging, and actually a given instruction could technically cross multiple pages and give multiple page faults. So consider fetching and decoding of an instruction which adds two numbers from memory. We can decrease the pain for something like that by using locality of reference. Also by hardware support which is needed for demand paging. Basically a page table and a secondary memory with swap space, and the ability to restart an instruction. So consider an instruction that could access several different locations, like a block move. We auto-increment, decrement the location. Do we restart the whole operation? What if the two sites overlap? So here are the stages in performance of demand paging, worst case. Trap the OS, save the user registers in process state, determine that there was a page fault, check the page reference is legal and determine the location of the page on disk, issue a read from the disk to a free frame, wait and queue for this device until the read is serviced, wait for the device and seek and latency time, and transfer the page. While waiting, allocate the CPU to some other user. Switch tasks or switch processes. When it's done, we'll receive an interrupt, save the registers and process state for the other user, determine that the interrupt was from the disk, correct the page table and other tables, and wait for the CPU to be allocated into this process again. Restore the user process, registers, process, and state, and then resume. So there are three major activities. Service the interrupt, read the page lots of times, restart the process. The page fault rate is between 0 and 1. If it's 0, there's no fault. If it's 1, everything is a fault. And the effective access time is 1 minus P times memory access cost plus P times the overhead involved. So we're not going to work through the computation here, but it's there if you want it. So this covers demand paging, and in the next section we will go on to part 2.